Okay, so this is the first lecture on partial differential equations. So partial differential equations is a very big field of mathematics with many applications in physics, biology, economics, a lot of possible applications. And it's so huge that it's impossible, I think, to make a course considering all reasonably important partial differential equations. So one has to choose necessarily. So I write down here some of the most important, just some of the most important PDEs, and then we will choose one of them, and then we will do some lectures on that, and maybe if there will be some time, we will do something also on some other PD. Okay, so typical PDEs, one should define the order, the type of PD, but let me just write for you this is called the Poisson Equation. It's a typical elliptic PDE, where this notation means the Laplacian of a function. So I think everybody knows, but just to, if U is in C2 of, say, some open set over N, then Laplacian of U at a point X is just the sum the U, the xi squared x, where omega, say, is an open and x is just as a definition. So this is, we will study this, we will say something about this. So this is given, say, and this is an equation maybe in omega. And possibly then one should couple this, which is a typical PD of second order, because these are two derivatives actually. One couple this with some type of boundary condition, which is very delicate to decide which kind of boundary condition one should couple with the PD. Typically, one possibility is, say, given G with some regularity, given F, given omega. So typical problem is conditions on omega, F and G. G is given, so F is given, and G also is given. This denotes the topological boundary. So sufficient conditions on omega, F and G such that this Dirichlet, it is called Dirichlet problem, say 1, has a solution in some class. If one wants to see this pointwise solution in C2, and then there is a delicate problem of saying how the boundary condition is attained. What does it mean that U is equal to G on the boundary? So maybe in order to be clear, we could decide that by this we mean that at any point X on the boundary, U of X, which is defined because it is continuous and defined on the closure, must be equal to G of X. Suppose, say, that G is continuous in some class G. So this is a typical problem of existence. Not only this, one could ask for uniqueness. What about uniqueness? So this, depending on the various PDEs that you have, the existence and the uniqueness problem are not necessarily separate, but in some cases you can first study, so you can study them separately, but not always. What about uniqueness? And then the most difficult usually is what about regularity? Regularity meaning that maybe a solution, maybe if f, say, is knows infinity, maybe the solution is more than C2, is infinity, maybe. This is typical kind of problems. This is an elliptic PDE. I don't want now here to explain why we call it elliptic. It depends on the signature of, I don't want to tell you now. So this is a typical problem. So, and it is used in physics, in electromagnetism, for instance, and in harmonic analysis. Another problem of interest here is the heat equation. So you have another PDE. Now there is a new variable here, which is, we could call it time. ut means t means the partial derivative of u with respect to t. Suppose that t is a function depending on the variable t and x. So say u is defined from some 0 capital T to r. So we have u equal u of tx. Everything here is scalar. I will not tell you anything about systems, okay? So u is a scalar function. It takes values in R. This PDE, again, could be asked to be valid, say, in some cylinder in space-time, where I decide to call t the first variable in Rn plus 1. So this object here is contained, say, in R1. Okay. And again, same kind of problems. So we have to couple this with suitable boundary conditions. In this case, the boundary conditions are not immediate. One could, so plus boundary conditions. Boundary conditions for this kind of problem typically could be a Dirichlet type boundary condition on the lateral boundary of the cylinder, say, so this is omega, this is t, so we have this time-space cylinder, if you want, and we could ask for, assuming here some given condition, say, but we also need some condition at time 0. This is time 0. Okay. So the boundary condition, this is one possible boundary condition for this kind of problems. No condition on the, usually on the top of the cylinder. Same kind of problems. Existence, which is non-trivial, under which condition on the data of the problem we have existence, uniqueness, and regularity. Be careful, this is usually the most difficult and deep part of all the story. Not necessarily disjoint from the previous two problems. This PDE is a way to model, for instance, the heat flow in a medium. Indeed, it is called heat equation. In some sense, it is a degenerate equation because of this first derivative with respect to a new variable, but only first derivative. Instead, here we have two derivatives, some sort of degeneracy. So this is another different, related to this, but somehow different PDE. And then another typical PDE is the wave equation, 3. is the wave equation, and which is can be written as this. Again, for now the boundary conditions are different. One could add some initial condition here, and maybe here also the initial velocity. Well, I don't want to enter now here, because just to tell you which are possibly type. So these are classical PDEs. This is called an hyperbolic second order PDE. This is called a parabolic. Hyperbolic. Second order. Also, this is second order. These are second order PDEs. This, as the name says, is related to the wave propagations. Okay, it's very important in physics. This kind of PD. Okay, these are second order. There is a big theory instead of first order PDEs. First order PDEs are expressions where the u appears only through its through u maybe and through its first derivative. So one typical in when say tx in say 0 plus infinity, say, or 0t times r, one space dimension, u equal u of tx. This is called an hyperbolic first order PDE. You see here it appears only first derivative with respect to x space and first derivative with respect to time. Another kind of famous first order PDE is this. So this is called the conservation law, and this is called Hamilton-Jacobi equation. These are first order, this is the gradient of u, etc. I mean, one has PDEs of first, second, third, fourth order, etc., etc. So one has to decide, each of these PD has its own theory of existence, uniqueness possibly, existence and regularity. So we have to choose. These two equations in some sense are close to each other, in some sense. So maybe on the other hand this is maybe qualitatively more different. So I have decided to, instead of starting from first order, because this, if I start from first order, I think I need all the course to study first order. This is the problem. So I decided to choose second order. So these are very important, but unfortunately we cannot say anything about this, sorry. So I also, for the moment, neglect the wave equation. And I go on into the details of point 1. Okay. So there is, in some sense, there is no time. Oh, notice that one could see, this is not very physical, one could see this operator, one could split it in somehow in the following form, say minus u xn xn equal, one could split dividing the, say, one pure second derivative, and all the others, say, minus equal, so sum from I to 1 to n minus 1, f. So in some sense, if one say that this is time, this should be sort of utt equal minus this. And this is some sort of qualitative expression similar to the wave equation, but with a very different sign. So there is a minus here. So this is not very physical, but it may be helpful to give it once in life to look at the equation in this form in very special cases when it is possible to apply a famous theorem which is called Cauchy-Riemann. So in principle, one could do it is not very useful, but just only for application of this theorem, one could have a look of the PDE of the operator, writing in this way, splitting one second pure derivative and all the others on the other side. Okay, let's go slowly. Some references. Maybe it's time to tell you some reference. Okay, so let me erase everything. Just keep the and this. So references, possible references on elliptic PDEs. There are famous references. Just this is one famous book. Then there is Evans. And then there are many other books. Okay. This is a book dedicated to linear. By the way, this is a linear PDE because U appears, the unknown U appears linearly. These books treat the case of linear and maybe non-linear elliptic PDEs also. Evans is, on the other hand, a general book not only on elliptic but also something on parabolic, hyperbolic, and something also first order. Okay. So let us start with the theory. So now this is called the Dirichlet problem. This is called the Poisson equation. F is given. Dirichlet problem because we have this kind of boundary condition. So we start by simplifying a lot. Okay. So the first simplification that we do is this. Okay. So we do this simplification and this. Oh, the reason for the minus here will be apparent during the computation. It depends on, one could write it as Laplace of u equals 0. I prefer to keep the minus for various reasons, but there is really no, one could avoid the minus. Okay? So minus is just a matter of convention choice. Okay, so first simplification. So let me give you a definition now. So definition is the following. So from now on, say omega is an open set. So let me, which could be the whole space, could be something else. Okay, we say that U, so let U in C2, which is here the most important assumption. Because for proving existence, the point will be exactly to prove that, to give some sort of clever formulation of this problem and find that a posteriori U is really C2, so that at each point you have this equality. But for the moment we are at the beginning, so suppose that U is C2, so this is a very strong assumption. Of course, if U is C2, this object is defined pointwise at any point. Okay, so there is no ambiguity in defining this object. If U is in C1 or in some subole space or in L1, L1 lock, whatever, then one has to interpret this equation in some other way, but of course not pointwise. Okay, not pointwise everywhere. Okay. Okay, suppose that this, so we say that U is a classical subharmonic function in omega if minus Laplace of U less than or equal than 0 in omega. What does it mean? It means this, when I write this, since U is C2, it means that at any x minus Laplace of U evaluated at x is non-positive. Okay? So we say that U is classical superharmonic somehow we have the less than or equal, sub and less than or equal. There is a way to remember maybe with the minus. So if unfortunately, if this is one of the reasons for which maybe it's convenient to use the minus, because no, if you don't avoid the minus, then you say that it's subharmonic if Laplace of U is larger or equal. So, we say that U is a classical superharmonic if minus U is classical subharmonic. And we say that UC2 is harmonic in omega. We say that U is harmonic in omega if it is at the same time subharmonic and superharmonic in omega. Okay? Okay, these sometimes are called subsolutions of the operator, of the PDE, and these are called sometimes supersolutions. Okay? The concept, so you see already from this very initial definition in which we assume the most we can assume, I mean this regularity, it's interesting to observe that we have transformed in some sense the PDE into a partial differential inequality. And this is crucial in this kind of problems because at the end, we will see, I don't know if there will be time enough, at the end, one way to produce a solution of this kind of problems is to use the so-called maximum principle and to define somehow a solution in between a subsolution and the supersolution, so something inside. So to use this idea, one has to define what is a subsolution, what is a supersolution, and try to look for a solution inside, in between. So this is somehow important if one wants to use the so-called maximum principle, which is valid for this kind of PDEs. Okay. So now the point is to try to figure out examples of this of harmonic functions. So you see, our problem for the moment is the following. Suppose that I give you omega, reasonable set, say a ball, in R2, okay, disk. This is a quite reasonable domain, open set. Suppose that I give you some function g, defined only here, maybe continuous. Or can I extend g? G is on the boundary only. Maybe it's continuous with some regularity. Can I extend it g inside in an harmonic way? No? You can look at this as follows. G is given. If I'm able to solve this, it means that there is u inside, which is harmonic, which coincides with g on the boundary. So this is called harmonic extension of g, which is by not trivial at all to say, okay, who knows? Can I, given G, can I extend it in an harmonic way? Who knows? Not clear at all. So this is a possible way to look at, to interpret this. Of course, let me remark, this depends on the choice of omega and of G. Now, let's simplify. So you see, in definition one, there is no G. Okay, I'm saying something only about the PDE, but not about the boundary condition. Okay, so let me simplify it even more. So let's try to discuss the problem, the free problem without boundary condition. Okay, I simplify it. Okay, now I am interested. So this is not anymore maybe called Poisson equation, but I want to concentrate with this kind of simplified problem. Okay, so this is the most simple case, but still is far from being trivial. So the question now is, what about free solutions on some domain omega of this kind of problem? Okay. So now let me give you some exercise for home. So home. So suppose that omega is convex. So convex open set in a Rn. Everybody knows what it is, right? Okay, let U be classical subharmonic, or maybe even easier, let me start with be classical harmonic. Let F, say in C2, be convex. Okay. Show that the composition of F with U is subharmonic. So try to do this exercise. This is a way to produce examples. If you have examples of harmonic functions, in this way you can produce examples of subharmonic functions. Okay? It is very important when you have a new PDE, or in general a PDE, to have as most as you can explicit examples of solutions. Very important to have solutions, explicit that you can see, and also maybe an explicit example of sub-solution and super-solutions. These are very important. Okay?
So what is the condition on F?
It is convex. It is convex and C2, just convex. Okay, convex. Okay. Okay. How can we say other examples? Now we need examples. Examples. Suppose that U in C2 is convex, omega convex, say omega convex, sorry, comma, U in C2 omega convex, then U is subharmonic. Like this. Why it should be so? If you have a you should see it maybe at home. I mean, if you have a C2 function, convexity means, for instance, one variable, but this is true in any variable. So u second larger or equal than 0 in one variable, just one variable. And so this means that we can produce subharmonic classical subharmonic. So we can produce in one dimension immediately. If you have to think about what is a subharmonic, maybe the first thing that one has in mind is a convex function like this. Okay, in one dimension. In any dimension, okay, convexity means that the Hessian so that we denoted this by the Hessian. No? So the Hessian is a symmetric matrix if U is C2. No? The Hessian is non-negative definite. And so, since the Laplacian is the trace of the Hessian, it's not difficult to see that also the Laplacian has a sign. Also the Laplacian must be non-negative. So this means a symmetric matrix, positive, non-negative definite. Okay, it's not a number, it's a matrix at any point x. Okay. So example. So harmonicity in one dimension. Let me tell you some more examples. Say suppose that you have omega equal r, say whatever, or a segment, or just an interval, say, or some interval. If you look for harmonic functions in one dimension, this means simply minus u second equal to 0. That in one dimension means simply that linear functions are harmonic. Okay. In one dimension. It is also clear that in n dimension, linear functions, say u of x equals some vector v scalar product with x plus some number. Okay, this is a linear function in n dimension. And it is also clear that this is harmonic. So graphs are hyperplanes. Graphs are lines or hyperplanes. It is clear that they are harmonic, but we need some more interesting examples. Okay, is this clear up to now? Are there problems?
Yes, but I have one question. What you are saying classical, like some books are using just this definition of harmonic?
No, this is not the very definition of subharmonic.
There are some other...
No, I insist on the word classical. I put it because there is a reason. If you look, sorry, I forgot about a very important book in PDs, let me tell you. Sorry, I forgot. So I added this in the list. It's for Mander. There is a sort of an encyclopedic treatise on linear PDEs, so various volumes, not only one. Sorry, this is just to add, just to add in the list. Now, there are various ways to define subharmonicity, and if you look, for instance, in certain books, the very definition of classical harmonic is just
is average.
Is
average is average.
No, I mean, well, I think we will see this. One possibility is to say that U say is upper semi-continuous, so you don't need to be continuous even. Subharmonic, upper semi-continuous, maybe with values minus infinity plus infinity, probably. And also now here maybe some authors ask that U is not identically minus infinity in any connected component of omega. Okay, but this is depends on the authors. But more interestingly now, one could give a definition, say, using the mean value formulas. So saying that U of x, say for instance, is less than or equal than its mean value on a ball, say N1. This is one possibility. But maybe the best is to so in this way you see there is no PDE. U is not even continuous, so I cannot write minus Laplacian, of course. So I have to write it in a clever way, forgetting the operator. And then, or also, maybe what I prefer is to define it by comparison with harmonic functions, or say, or U defined, but we will see, I think, this via a maximum principle. Maximum principle against harmonic functions. I stress harmonic functions. So I prefer this. So let me erase this one. This is one possibility. But let me stress that also this one. So it is in a sense says that U is subharmonic. Say if okay, it is some kind of continuity, and if on the boundary of any sum on a ball inside here, if it is not larger on the boundary of the ball of an harmonic function, then it must be not larger than it inside the ball. No? So it is something like, this is the first lecture, I cannot be, so say that if U is less than or equal than H with H harmonic, and this on the boundary of some ball, P is any ball, say, contained in omega, see? And H is harmonic in the ball, then U must be less than or equal than H in the ball. So it is by comparison, which is, by the way, the same way we define what is a convex function. Because what is a this is the same principle for which we define what is one possibility to define what is a convex function. Because a convex function, say, something like this. Suppose that I know that here and here, this is a linear function. Here and here I am above, then I must be above also inside. Okay? So if you know that I am above here, then I must be above. So if here and here this object is above this, then it must be above also inside. So this is a comparison way to define a convex function. Now, for subharmonics, instead of using linear functions, like is what you use for convexity, instead of using linear, you use harmonic. Okay? This is what I know, at least what I know, one way to define what is a subsolution, subharmonic. So you see, and now I put classical, because I want to stress that I'm assuming this. But the theory, the good theory one should do is starting from here. But I want to reach this point only when I have already understood the classical theory, otherwise. Okay, this is, and then this is not only the way, I mean, because there is another viewpoint which is related to the fact that actually this is a stationarity condition for an energy functional. So this, we will see this, not today. And this express stationarity, whatever this means, let me be very rough. with respect to an energy function which is called the Dirichlet integral. So stationarity with respect to an object which requires much less regularity to be defined. Okay? So in some sense there is a way to, at least under certain conditions, to transform this PDE into a minimum problem somehow, or with some boundary condition, some more term, with respect to an energy function. If you should see the problem in this point of view, which is called the variational approach to this kind of elliptic PDE, then you can define what is a sub-solution and super-solution only looking at energy. Which means that a sub-solution is something which is a minimum only with respect to perturbations from one side. And super-solution is a minimum which is minimum only with respect to perturbation from the other side. And then these are generalization of classical subharmonic and superharmonic functions. So let's go slowly. So you see, the answer is there are at least two other ways to define reasonably what is a subharmonic function without writing the PDE, minus Laplace, never. In this way I don't write any operator, no derivatives. And here, what I need, I mean some sort of gradient, but not the second derivative, just the first derivative. And this is of importance because when you want to study existence, you cannot pretend to study existence from the beginning of a so smooth solution. Maybe you are able to find a solution in a larger class of objects, then a posteriori is C2, but in principle could be not C2. This is the reason, okay? Okay, so this is the... So there is so the one-dimensional case is somehow trivial for the moment. So linear functions, or convex or concave, of course. Subharmonic and superharmonic, I don't see the difference between convexity in one dimension and linear functions. By the way, in one dimension, the only functions which are at the same time convex and concave are the linear functions. Okay, in just one dimension. Maybe this is true also in any dimension. What is a very important case is n equal 2. N equal 2 is special in the theory of harmonic functions. It's very particular, but it is so important for the reason that it is related to complex analysis. So we cannot avoid to say something about this, okay? So let's see quickly which are some of the results which relate harmonic functions with holomorphic functions, okay? And in this way, we will have a lot of examples of harmonic functions. Okay, because there is a relation between harmonicity and holomorphicity. Okay. Okay, so let me tell you an exercise that we should do here. Exercise, I don't know, 1, 2, 3 maybe. Okay. So let omega say be an open set. And now we can identify this C, and let F be holomorphic. Holomorphic in omega. Holomorphic for me means that, say, if I write, well, I think everybody knows, right? But just let me repeat it. So if I write f equal u plus iv, where u is the real part and v is the imaginary part of f, and I write so u as u of x and y, so z is equal to x plus iy, and v equal v of xy. Okay, so for me holomorphic is, for instance, to ask that u, what does it mean? It means that u and v, say, are C1, they are real and are C1, and the f over dz bar is equal to 0 in omega, which means, so the f over dz bar is by definition, I think, 1/2, I think, the f over dx minus 1 over I think is the f over dy, something like, with minus 1 over I, yes. Okay, and this translates into a system of two, I think you know, no? Ux equal to dy, ux equal to dy, Okay, these the famous Cauchy-Riemann equations. Okay, so we can, if one likes the real way of writing the problem, one can simply say that u and v must be C1 and they must be solutions of this system, which is a system of two linear first-order PDEs, but it's a system. On the other hand, if one wants to look maybe more intrinsically at looking at C, one should say that f is differentiable in the complex sense, and this must be equal to 0 in omega. Depends on the way. Okay. So then, u, and so let me write it as before, u plus, in this identification, u plus iv, then u and v are harmonic. So in this way, if this is true, okay, if there is a way to produce a lot of harmonic functions. For instance, I don't know, so let's see examples. Take f of z e to the z, where clearly, by this condition, that function is harmonic, is a holomorphic, sorry, in the world C, is an entire holomorphic function. So I can write it as e to the x cos y plus I sin y. Okay. And so we can check that u of xy equal, for instance, x cos y, and v of xy equal u of x sin y are harmonic in the world space. Okay, these are not trivial examples of harmonic functions. Okay. Or say f of z equals z squared. So this is equal to what? I don't know, it's x plus iy times x plus iy. So we have x squared minus y squared plus I plus 2i xy. And so what I'm saying is that other examples of trivial nonlinear harmonic functions are those. Okay. And so on and so forth. Fz equals z cubed. Okay, do this at home. Other examples. So we can produce a lot of examples of non-trivial harmonic functions. Okay, so let us try to develop a little bit about this exercise 3. May I erase? Okay, so this is not difficult. So we know that indeed we know that this system of PDE must be satisfied in omega. We also know that U and V are not only C1, they are also much more than C1. Actually, they are C infinity, actually they are also analytic. Okay. So, and so U and V are even more than that, say, from the theory of holomorphic functions. Okay. They are much bigger. So this means that once we know this, we can differentiate. We know smoothness. We have smoothness enough. We can differentiate with respect to x the first one, and with so if I differentiate with respect to x the first PDE, we get equal v of yx. If I differentiate with respect to y the second PDE, I have uyx equal minus vxy. But on the other hand, we have smoothness enough. Therefore, this is we can exchange the order of derivative under this regularity assumption. So, and this means that sorry, this is y, uyy, yy, xy. Okay. So this means that now, if you take the sum of the two, must be equal to 0. Okay. And the same check at home, that is true for V. The same is true for V. Okay. So this is, again, we need examples. So otherwise we cannot go on. These, in 2 dimensions at least, are interesting examples. Let me tell you something more about this. So this is clear? Okay. So let me tell you something more about this. Now it's interesting to ask a more difficult question. So we have seen that if f is holomorphic, then u and v must be harmonic. And now, so there is a sort of opposite question. So suppose u in C2, so always in 2 dimensions, is harmonic. Can we find V? Does there exist V harmonic in omega such that U plus IV is holomorphic? No? Some sort of converse question. No? Do you know the answer? Have you already seen this kind of problems?
We can find
Everybody knows? Ah, okay. So let me. So in general, this question is not a positive answer. It's not always possible. So, but there is a sufficient condition on omega for which this. Do you know which is the sufficient condition on omega for which this is possible? Huh?
Correct.
No, not connected.
Convex.
No. Ah, okay. Convex. It's true, but it's a little bit too.
Starship.
Again, this is true, but it's a little bit too restrictive.
Simply connected.
Exactly. Okay, so maybe it's better to recall the theorem. So if omega is simply connected, such a V exists. Okay. And it is called the conjugate harmonic. And it is called a conjugate harmonic of U. And I think that also F in this case is determined up to a purely imaginary constant. There are examples, maybe all over. So if omega is not simply connected, take omega equal the pointed complex plane. Then V does not necessarily exist. This is the situation. Have you already seen in your courses this kind of? Because if you have seen, I can go on.
Yeah.
Oh, so you already know. So this is fine. Okay. Okay. So this is in this way we know something, and we have in mind examples. So now let's go back to the. I for the moment quit the complex world, and I go on in the real world in n-dimensional, however. So in order to try to find examples, we look in a Ren now in n dimensions. So not anymore confined on the complex case, but in any dimension. It's natural to look for special solution. You have a PDE, you don't know what to do. You don't know what to do, so it's very natural to look for functions which have some sort of symmetry. Okay, like what we do, say, in ODEs. Sometimes it happens that, okay, we have an ODE, we don't know what to do, we look for solutions, say, of the product of two variables or whatever. I mean, special kind of solutions with some symmetry which transform the PD into an ODE. This is the idea. Okay. So it's natural to look for special solution. So we impose some sort of symmetry in the possible solution which transforms the PD into something simpler, in this case an ODE. Okay? It looks for special solutions. So in this case, radial solution. we look for radial solution. What does it mean? So we look for u of x of the form v, not of x because it's too much, but v of modulus of x, normal x. Okay, so let me indicate, for some strange reason, this norm of x is just the distance from x to the origin. Okay, so I look for v of dx. Okay, and v now is something which is defined from 0 plus infinity into, say, r. Okay. So let's see how the PD. So I'm not writing the Laplacian in polar coordinates. I mean, I'm writing it in even simpler coordinates because my v does not depend on theta, but just on rho. Okay, just on rho. The usual notation is called this rho. Okay. So what do we have to do? We have to write the Laplacian. So remember, my notation is, this is the partial derivative of u with respect to xi. I is from 1 to n. Okay. My notation will be this, and the second derivatives will be okay. So the Laplacian is what? Well, the Laplacian is, so in order to compute the Laplacian, we start to compute this. So help me to do this computation in terms of v. What does it mean? No? So if I fix I from 1 to n, what is this in terms of v? So I transform now the PDE minus Laplacian of u equals 0. I transform it into an ODE with respect to v. Okay. So help me to compute this.
V prime.
V prime, exactly. Of v of x.
Times xi over
And the
xi.
derivative
Yes, and what is the derivative? So
Over it's no.
exactly. So provided. So there is a first restriction. So if we want to go on in this computation and we look for smooth solutions, we have a restriction on omega because we can work in some omega which has not the point the origin is for which the origin is not in omega. Okay. So maybe our omega could be from in this kind of discussion because of this problem that this is equal to xi divided by this, and in order to divide by the norm of x we need that x is non-zero. Okay, so omega, say, is Rn minus 0. Everybody agrees with this expression of everybody's no problems about this? Is clear? Okay, perfect. So let's go on now. Let's go on computing, say, the ij element of the Hessian out of the origin. So let's compute that one. So help me. What do I do? V second. Yes, V double prime. V second dx times xj xi divided by x squared plus, now what happens? Now it's more delicate. What happens to the so we have to compute this I and j. Given I have to compute this derivative with respect to j. What is it?
Minus xa over modulus.
And then?
Just again 1 over 2.
Now you have to be careful.
It's the same.
No, not quite, because there are two terms, right?
No, this is a cube.
No.
Should be.
J are this.
Okay, let me write it for you, if you agree. Do you agree with this?
Yes.
Everybody agrees, because there is the risk of making a mistake. So please check that what I'm writing is correct. Is it correct?
I believe you.
No.
It's not correct. What is the mean first step? This delta what?
This delta ij is the ij element of the identity matrix. Okay, so you take the identity matrix 1, 1, 1, etc., 0, 0, and take the ij element of this. I denote it by delta ij. It's a sort of standard notation. Okay, so this means that it's simply 1 if I equal to j, 0 if I is different from j. Okay. Just a definition, a very simple expression. So let me check. If I differentiate xi with respect to xj, I get delta ij. And now I have xi, and I have to differentiate 1 over modulus of x with respect to xj. So what is this? Is x minus 1. So this is minus 1 x minus 2. Okay. Minus 1 minus x minus, x minus 2, and then the derivative of the absolute value, of the norm. Okay, so which is minus x minus 2 xj over modulus of x. Okay, and so with this, right?
3.
Huh?
Modulus 3.
Minus x minus 2.
Is it 3
So
or 2?
the-
The one you written in the first expression. Is it 3 or 2?
Oh, we have to check.
No, this is not minus 1. This is a square root of something of minus 1 over 2, and this.
Huh?
It's not.
Yes, it's okay, no? I think everything is okay. So once I put this is minus 2, plus 1 is minus 3, and so indeed this is 3, no, it's not 2, this is 3, eh?
Yes.
This is 3. Okay. Okay. This is just for the computation of this object. Okay. And now I have to take the trace, because the Laplacian, of course, there are various ways, sorry, I should have told you before. Let me remark that one way to write the Laplacian is, of course, the divergence of the gradient. Okay. Another way is the trace of the Hessian. Nice. So now we have the. So where is the expression? Let me write it here. Okay, so it is written here, I think. So it's v second dx xi xj divided by x squared plus v prime dx multiplied by that matrix. So sorry, delta ij, delta, there is no space here, minus xi, xj, sorry, it's small blackboard, so I try to be, we have this, okay. This is the generic ij element, and we have to take the trace, which means that we have to sum over the repeated indices I equal to j. Okay. So, in some differential geometry notation, one should write this. If I repeat the index, this automatically means that I am summing from 1 to n. Oh, okay, this is a notation. Doesn't matter. I mean, it's a way to simplify the symbols without writing the sum. I mean, one usually sums over repeated indices. It doesn't matter. It's just a convention in differential geometry. So we have to compute this right-hand side. Okay, let's do this together. So V second does not depend on I and j, so this remains as it is. Now we have to sum xi divided by this. What is the result? 1 is the norm squared divided by the norm squared. Perfect. This is very easy. Second, sorry. V prime goes outside of the sum. And then we have to sum over I equal to j this. So what happens? What happens to this? Help me. So here what do I have to put? N, because the trace of the identity is n in n dimensions. Okay, do you agree? Okay, n divided by d of x. D of x, oh yes. And then I have minus 1 over norm x. Sorry, there is no reason for writing d of x. I don't know, I have written d of x. Maybe there is a reason now. Okay, so let me write it here. So this is v second d of x plus v prime d of x times n minus 1 divided by d of x. Oh, this has, by the way, a geometric meaning, maybe. It is the Laplacian of. This is the mean curvature of the sphere. Curiously, mean curvature of the sphere of radius x. No, because each principal curvature is 1 over the radius, but this is an n-dimensional surface, and you sum up. Without mean curvature is the sum of the principal curvatures. It's not divided by the mean. I mean, it's just the sum. All curvatures are the same. It turns out that this has a geometric meaning. It's a mean curvature of the sphere. Doesn't matter. That's maybe why I wrote D. So we have to so if we are looking for a radial solution, this means that we look for a V in C2, see, satisfying V second of rho plus V prime of rho multiplied by n minus 1 over rho equals 0. And rho must be positive. Because we have excluded the origin. Okay. Well, this is not really a second order ODE, but it's more precisely, I would say, a first order ODE, right? Yeah. But before going on, let me separate one easy case. if it is maybe a little bit too easy, but I prefer to tell you because we are. So the easiest case is when n is 1 dimension. Why not? So n equal 1. This second of rho equal 0. Solutions?
Maybe
No. That's why I know this confusion, because it's normal. I mean, somehow in some sense it's natural. It's because we are looking for solutions which are in one dimension are simply even, because they must depend on modulus of x. So nonlinear function unless you are 0. Solutions. Linear is almost correct. You have to modify it to make it depending only on modulus of x. I mean, his solution would be, he's suggesting, as far as I understand, this, right? But this is clear, it's not depending on modulus of x, it's depending on x. So which is the obvious modification?
just change modulus of x, but it wouldn't be secret.
This is the obvious modification.
But we lose regularity.
Origin is excluded, and this is a crucial point. Okay, so v of x in one dimensional, let me go back to the notation x. So this is ax plus b. Now, it is convenient, but one can choose BA, etc. But there is a natural choice, B equals 0 and A is minus 1 over 2 pi, 1 over 2, sorry. So, usually, we take B equals 0 and A equals minus 1 over 2. So let's see this function. Minus 1 over 2. Okay, some sort of so there is a singularity at the origin. This is always, as a sign, is always less than or equal than 0. So let me do an exercise now before going on. So remember that we have not finished our computation. We have to consider the more interesting, actually much more rich case of n equal to 3, etc. But I want to go on to make an exercise in one dimension. Okay. Okay, so let me find, I don't know what the exercise is, of course. So compute, so exercise 4, maybe. So compute minus v phi second dx for any phi infinity with compact support. Okay. So V is Lipschitz, obviously. So V prime is defined at all pointwise defined up to the origin. So V prime is defined, so which is the shape of V prime. So here I am increasing, here I am decreasing, some sort of like this, no? Minus 1/2, 1/2 and minus 1/2. And V prime, say, is a function in L1 log of R. Even more, I mean, it's defined everywhere up to this point. Here is not defined. In 0 is not defined. B prime in the sense, pointwise sense. But V second is not. I mean, we know what is V second. The V second in the sense of distribution. V second in the sense of distribution. So, because I mean, we cannot, I mean, V second pointwise, I mean, would be 0, plus infinity, or maybe minus infinity in this case, and 0. So it's not really a function. So V second is not a function. Okay. Did you study? Did you say something about distributions? Maybe
Yes.
not.
No, seminar, just come saying.
You made a seminar, so you know everything about distribution. No. Almost everything. Almost everything. The second is in the sense of distributions. So maybe you can tell me what is the second in the sense of distribution.
No, we didn't.
No, you should know. I think you should know.
It's just 0 and.
No.
Is that
Yes. Okay.
0 then.
In the sense of, very nice that you made a seminar. So let's try to, in the sense of distribution, the second is what? Is Dirac delta at 0, but positive or negative?
I'm not sure.
No, you should know. I mean, is this an increasing function or decreasing function?
Decreasing.
Right,
It's
so
not
it is-
negative. Minus.
Hmm?
Okay.
So morally, what should happen? I mean, you see, this is not differentiable in this point, at least in any reasonable pointwise sense. Say, but we can give it a meaning, still differentiate in the weak sense of distributions. What we should expect is something decreasing. So if there is a Dirac delta, there should be some negative number in front of the Dirac delta, but by y is 1, this coefficient here, minus 1, sorry. But just because this height is 1. This is 1/2 and 1 minus 1/2. So the height of the jump is just the coefficient in front. No? Now, so you see this function here has a V second, which is not a function. What does it mean? It is not it's not representable as an L1 log function. But in any case, it is this object, which is a measure. Now, you see from this expression, I have chosen this 1/2, minus 1/2, exactly because I like to have minus Laplacian equal +1 times Dirac delta. Of course, if I change the constant here, I could take any constant, A, I don't know, A equal whatever. But if I change the constant here, then the constant here changes. Only the choice A equal 1/2 gives me minus Laplacian equal delta at the origin. So this is the reason, a posteriori, the reason for which we normalize constants like this. Okay? And we will do this in any dimension, but I think that in one dimension is already meaningful to understand what's going on. So we have found a harmonic function out of the origin, which is symmetric, even in one dimension. However, it has a singularity at 0. Okay. Not only this, there is one information more is that this always does not change sign. Is always non-positive. The meaning of exercise 4, now that we have understood that morally we should have this. We expect this in order, because of your seminar, because of our marks, we expect this. But this is the rigorous way to say this, is to show that this equals the rigorous way.
The integral of this times b prime
Delta.
Yeah,
V dash phi dash.
yeah, this
Which is the way, which is the rigorous way to give a mathematical meaning to this expression. Exactly. So for any test function, because this is what? This is the duality between the test function and the Dirac delta at 0. This is exactly a definition, or if you want, one definition of what does it mean Dirac delta at 0. It takes a test function, actually a continuous function would be enough, and
There
evaluate.
is a minus sign.
No.
No, because
is the other side.
Ah, okay.
I put the minus here. Okay, so if you don't know what does it mean this, the definition of this is exactly the content of this exercise. Prove that for any test function phi, say in C infinity, but C2 would be enough, actually. For any phi, if you compute this, now this is the left-hand side is very well defined, because phi has compact support. Therefore, also phi second has compact support. So this integral is on a compact set, and V is bounded on a compact set, phi second also, so this is finite. So no problems in defining the left-hand side. Okay. So why don't you do by yourself this computation at home? I suggest I said that you should try, because this is maybe the first, you have not studied yet distributions, which is a very huge subject and difficult, so we have no time, but how should we do? How should we? So this is home. But how should you do? How should you do to do the exercise? So you start with this minus integral over R. We have already observed that.
We integrate by parts and
Okay, we integrate by parts. So this means that correct. We integrate by parts. So we could. This is a Lebesgue integral, right? So it does not see sets of zero measure. In particular, we can integrate out of the origin, which is one point only, and there V is perfectly. We can surely integrate by parts, and there is no problem in writing this dx. And we have a minus, which becomes a plus. And now what do you do?
integrate by parts again.
The point is that if you integrate by parts again, you should put. Remember that there is no boundary term here. Why there is no boundary term?
Because it is a compact.
Because phi has.
compact
This is crucial. Don't forget that we are localizing in a compact set. Otherwise, we are lost. Okay. So no boundary term. At infinity, everything is zero. Now the idea would be, okay, why don't we do it once more? But then there is a big problem here, because who is V second? We don't know exactly. We want to find it somehow. It's not really a function for which we can. So what do we do?
Can we use this V
Hmm?
prime?
V prime, V prime is in that one lock. It is 1/2 at negative x and minus 1/2 at positive x. It is almost everywhere defined. And if I integrate on a compact set, this
We can separate this integral to sum of two integrals.
Exactly.
That's it.
Why not? This of course can be done. So the integral, as you suggest, plus the integral 0 plus infinity, right? dx, and on minus infinity 0, V prime is a constant. Okay, is 1/2. and on 0 plus infinity, v prime is a constant. Now what do we do?
We use the integration function.
Now phi is C1, phi prime is C infinity C. So we can use the fundamental theorem of integral. So this is phi at 0 minus 0, because phi has compact support, so there is. So this is 1/2 phi at 0 minus 0. And now this is phi at plus infinity, which is 0, minus phi at 0. With the minus in front is the plus. And this, sorry, at the end I made the exercise, so this is phi of 0. So this rigorously show that, sorry, I did the exercise, gives a perfect rigorous meaning to this expression. Okay. So what does it mean to solve this in the sense of distribution? We found the solution, which is a sort of function like this. Okay, I think that for today it's enough, so stop, excuse me.